Welcome to this session, which will be dealing with the milling operation as one of the most important manufacturing operation. I really hope that you enjoy the webinar and you can get new ideas about how to monitor your system, that you will have more improved knowledge about milling operation, and finally and hopefully you can connect force signals and torque signals to your machine and utilize intelligent machining to control the process with force and torque measurement. So let's start. The agenda is divided into 5 chapters. In the beginning, we will talk about what milling is and what do we really measure. Later on, we will look to with what I can measure, talk about some of our products, and then we will move on to what important parameters to consider in force measurement, and at the end, why do we measure forces. Let's start talking about what milling is. Milling is, as you know, is a high dynamic process. The cutting motion is carried out by the rotating tool. As you can see here, you will be seeing the video soon. And the field motion is carried out by the linear motion of the machine table or machine spindle. As you can see here, you have the cutting motion carried out by the tool itself, and the field motion is carried out by the linear motion of the machine table and the spindle. There are different types of force measurement opportunities. You can either use stationary dynamometer, as you can see here, or you can utilize rotating dynamometers, an integrated tool on the rotating dynamometer, as you can see here, which the cases. There are different types of milling operations. The main ones are face milling, peripheral milling, and end milling. In the face milling, as you can see that you have different types of inserts located in your cutter body when you are machining the surface. You have peripheral milling. Depending on the direction of the motion, you can have up milling or down milling, and then you have end milling. You have also different types of tools. There are tools where you have inserts located on, and there are tools where the cutting edge is geometrically defined on the tool itself. The milling operation is an interrupted process. The chip thickness varies from the start of the engagement until the end of the engagement. The cutting forces are highly dynamic, so it gives a high demand on the machine stiffness and damping properties, which we'll talk more later on. What do you really measure then? If you look to this schematical view here, you have the dynamometer, you have the part to be measured, you have your tool. Because of the rotation, you will have a torque, and because of the feed from right to left, in this case, you will have a feed force, and then you will have a normal feed force, the force which is normal to the feed force, and you will have a passive force. So, if you are measuring with the stationary dynamometer, you will be measuring these 3 force components: feed force, normal feed force, and passive force, as we mentioned here. But if you are utilizing a rotating dynamometer, you will be also measuring the spindle moment directly, and the passive force, and also the forces in Fx and Fi, which are different compared to the forces measured with the stationary dynamometer. We will be mentioning this later on. Let's have a look on the force components we measured with the stationary dynamometer. Let's start with face milling. You have the, as you can see, the milling tool. And if you look to that picture from the top, as you can see that you have the rotation of your milling tool, the unmachined surface is there, and then you have the machined surface. So, due to the rotation of your tool, you have a cutting velocity, as you can see here, the blue vector, and because of the feed, you have the feed velocity, as you can see here. And you have the force component Fx, which is shown here as the green, Ff here in the horizontal direction, and then you have the normal force to the feed, which you can see in the vertical direction, in y direction, as you can see here. And by utilizing these force components, you can calculate the active force, which is the vectorial summation of the feed force and the feed normal force. And then you have the cutting force, which is the tangential force, and you have the cutting normal force, which is normal to the cutting force. And by utilizing the feed force and feed normal force and the rotating of the axis, the angle, you can calculate the cutting force and cutting normal force. If you look onto the rotary dynamometer, it is a little bit different compared to stationary dynamometer. In the rotary dynamometer, the coordinate axis is also rotating, as you can see, x and y of the rotating dynamometer coordinate axis compared to the rotating to the coordinate axis of the stationary dynamometer, as you can see here. So with the stationary dynamometer, as you remember, we were measuring fx and fy, which are shown here with the green vectors. You still have the cutting velocity because of the rotation. You have the feed velocity because of the feeding. And now if you look to the x components of the force measurement from the rotary dynamometer, as you can see, the blue vector is here, and that is different compared to the green one, which is the force measurement in the x direction with the stationary dynamometer. If you look to the y component of the RCD measurement, you can see the blue vector here, and that is also different from the stationary dynamometer. So if you look to the active force, that is actually still the same. This is the vectorial summation of the force component in x and in y direction, as you can see here. And that is actually, again, the vectorial summation of the cutting force and cutting normal force. On top of that, you are also measuring the spindle moment, and by utilizing the radius of your tool, you can calculate the cutting force very easily. And again, by utilizing the active force and the cutting force that you have calculated, we can calculate the cutting normal force. Please observe that the forces in x and y direction are different than what you measure with the rotating dynamometer and what you measure with the stationary dynamometer. Let's have a look at one application here, Facemilling with 2 inserts. You can see here, it is made with a stationary dynamometer, the measurement. You can see here, the cutting conditions, the force measurement. As you can see here, the Fy is in the horizontal direction and Fx is the vertical. You have the active force here. You have again the cutting velocity and feed velocity. So if you look to the measurements of x and y and zeta, you can see that the x force almost goes to 0. That is one insert is almost leaving the machine surface, and the second one is starting to engage. You have almost 0 force components, as you can see here. And then if you look to the y force component in y direction, it is both negative and positive values, and that is because when the insert starts engagement, as you can see, you have the y force components is one direction, and after 90 degree here, when it passes up here until 180 degree, the force component direction will be changing. That's why you have positive and negative values in the y components. And then you have the force component in the zeta direction, and that is the force which is pressing the machine tool away from the machine surface. Let's compare the active force, which can be calculated with the help of the force components that can be measured with the rotary dynamometer and the stationary dynamometer. Let's take the case of Facemilling, as you can see here, with 4 inserts located on, and then you have the cutting conditions. The type of the rotary dynamometer is 9123, and the type of the stationary dynamometer is 9255. Let's have a look to the active force comparison. As you can see, the blue force signal coming from the rotary dynamometer and the red force signal coming from the stationary dynamometer. As you can see that the amount of the details is almost the same. There is a slight difference in the measurements. due to the fact that we have difference in the natural frequencies. It can also be the mounting, which is different, of course, in two cases, and the cutting conditions can also affect the differences. Let's have a look to this slide where you can see that the torque can be directly measured with the help of the rotary dynamometer, as we said before. This is the case where you have a milling tool with a diameter of 10 millimeter, you can see here, with 4 cutting inserts located on that, and you can see the cutting conditions. So you have the torque signal, as you can see, with the function of the time. And if you can zoom into the torque signal, as you can see here, you have the torque values acting on each insert. You remember that we had 4 inserts on the cutting tool. The red lines are representing the start and end of the rotation. As you can see quite a lot of details. You can also, by utilizing our software DynoWare, can get polar diagrams to understand the torque distribution around the tool. As you can see, the torque values around the geometry of your cutting tool. Let's have a look too with what I can measure. Talk about some force measurement technologies. As we mentioned in the first session when we were talking about turning operation, there are basically mainly 2 technologies, either piezoelectrical technology or strain gauges. The piezoelectrical technology enables highly dynamic measurements due to the high natural frequency of the sensors. It enables measurement of small force fluctuations, and it gives wide measuring range, and it has high precision due to the linearity and hysteresis characteristic. And the product life is often much longer than strain gauges. On the other hand, strain gauges enables us to perform more static measurements during several minutes, longer times. The temperature influence is easier to compensate, and we don't need highly insulating cables as we need for the piezoelectrical sensors. If you have a look onto the dynamometers, remember we have mentioned that you can either have stationary dynamometers on the table or the rotary ones. So you remember we have mentioned already that the coordinate system in the rotating dynamometers, they are also rotating in comparison to the coordinate axis. As you can see, for the stationary dynamometer, they are stationary. If we have a look on the design of the rotating dynamometers, it also includes a ring sensor which is rotating in this case, and it consists of 4, as you can see, crystal layers, 3 layers for each direction, x, y, zeta, and 1 for the moment measurement, compared to the stationary dynamometer, which often consists of force measurement sensors here, force sensors, which enables you to measure forces and also calculate the moments with the dimensions of your stationary dynamometer. As we said before, depending on if you are utilizing on your machine table a stationary dynamometer or rotating, there are different options. And we will talk a little bit more about the 9109 with high frequencies, which is very important for micro machining, for instance. If you look to this plot here, it is showing the high frequency, natural frequency of microdial up to 15 kHz, which enables us having a measurement range up to 5 kHz. And of course, that enables to utilize high rotations up to 150,000. And that is important when you are making micro machining, where you have very high RPMs, small forces. As you can see, the forces are around plus minus 20 Newton, but you can still capture, as you can see here, you can still capture details on your tool in your force measurement and optimize it. If you talk about the measurement chain, depending on if you are using a rotary dynamometer or a stationary dynamometer, you have different options. For the rotary dynamometers, you need to have a signal conditioning, data acquisition system, and the connection to your PC. For instance, our software DynoWare. If you have a stationary dynamometer, you can connect it to amplifier and the data acquisition system, or directly to lab app which is a combination of amplifier and data acquisition system. Later on, connect directly to your PC. Machine connection, regardless of if you have a rotating dynamometer or you have stationary dynamometer with different measurement setup, you can utilize your analog signal and connect directly to the machine by utilizing the fast NC input and outputs. Or you can use an industrial amplifier, for instance 5074, and then you can get the signal with the Profinet protocol and connect directly to the Profinet protocol and input of the machine. And then later on, now it's time to make some programming. This is only one example on how you can utilize synchronous actions. It's an advanced programming language in the NC. So what we do is that we first start filtering the input signal, which was, if you remember, input 1. Now we dedicate it as fx and assign it to any parameter 25. And with this equation here, we are making filtering and moving average. And the smaller the value, the stronger the filter is. So the summation of these two parameters should be 1. You can do the same thing in other signals, of course. And here is, let us say, it is the f zeta. Then you need to reset the amplifier, start and stop during and after the measurement. And you can utilize this commando here. And you may need timer due to different programming options later on, where you put on a reset the timer here. So then let us make a very simple tool condition monitoring. As you can see here, we assign R51 a limit which is 100 Newton, and we tell to the machine that once the force value in F zeta direction goes over 100, give an alarm, and the machine will do that. So we build a very simple condition monitoring and toolware alarm with the force signs. Let's talk a little bit about more important parameters in force measurement. As we said before, milling is a highly dynamic operation. You really need to understand and investigate first the dynamics of your system to understand what does a force measurement tell you and how to set up a correct data acquisition and signal analysis. You can perform a frequency analysis to understand the nature frequencies of your machine and process. You can place an accelerometer on your different machine parts and make measurements when the machine switches off in order to understand the frequencies of the mechanic itself and also any disturbances coming from outside machine. You can perform measurements when moving slides, when rotating spindles, when coolant pumps on and off, and so on and so on. And at the end, of course, you can make the measurement while cutting. And then you will have a good understanding of which frequencies are coming from what. And you can take this one step further. You can perform model analysis to understand the deflection modes of your machine part with frequencies and amplitudes, with the help of, for instance, accelerometers and hammer in this case. So when you follow this and then really understand and investigate your system, then you will really understand when you make the force measurement what is what. And of course, it's also an important procedure for setting filters and sampling rate when you have this understanding. So the first step, as we said, determine the usable frequency range, and that can be done by the system identification. So you have to get a good picture of the frequency response of your system. And of course, this can be done, for instance, with accelerometers and hammer with force sensors also. So you know exactly what kind of nature frequencies your system has. And when you have that, then you can place your low-pass filter, for instance, in your amplifier or in your post-processing in order to have this usable frequency range. And the low-pass filter can be placed around third and fifth part of the natural frequency, as you can see here. And this will also determine your usable measurement range. And when you know the measurement range and your low-pass filter, then you can define your sampling frequency, and that should be at least 5 to 10 times the cutoff frequency of the low-pass filter. And of course, then you can perform your signal analysis in your post-processing. This is a force measurement, as you can see, and we can perform partial FFT on that, and that is possible in our DynaWare. Why is that important? Because as you can see that the force measurement consists of different types of frequencies, and when you make the FFT analysis, you can see which kind of frequencies you have up to which amplitudes in your force measurement. And if you have done the investigation of the frequency response function of your machine and setup, then you know exactly what kind of frequencies are coming from the machine electrical system, the machine mechanical system, any possible equipment that can be affecting your measurement, and what kind of frequencies are coming purely from your chip formation. Choosing the right RPM is very important. We do not want to end up in resonance, so that's why we have to really understand the frequency response of our system. As you can see that this is a force measurement done by just exciting the system in the time domain, and you can convert it to the frequency domain, for instance, by utilizing our software. And then later on you can utilize the equation, as you can see here, the tooth passing frequency with the function of the RPM, and that RPM should end up in a frequency that is not close to or inside of these regions where you have the natural frequencies, because if you are too close or if you are inside, then you will have resonance vibrations. That's why you really have to follow the step by step and understand the frequency function of your system. Let's have a look of the type of the mountings here. So the dynamometer is mounted on the granite table by clamping gloves in one setup. In the other setup, as you can see, the dynamometer is installed with the screws, and in the third setup with the VC1000. And if you look to the now, when the force is excited in the zeta direction, the frequency response of our system, depending on this different type of clamping, will be different, as you can see in this plot here. And then you have the phase shift, can be seen here. So it's really important to understand the response of your system, and it is depending on the mounting, of course. What about the additional mass? As we know, the additional mass will also influence the natural frequencies. So in this setup, you can see the stationary dynamometer 9255 here, and then we have an additional mass and another dynamometer which is 9256, and then you have your workpiece and milling tool. So we have an additional mass of 35 kilogram in this case, where the 9255 will be being affected in this case. If you look to the force signal in X, Y, and zeta direction, you can see the red force signal coming from the 9255, so that is coming from the stationary dynamometer on the bottom, and the force signal 9256, the blue one, is coming from this dynamometer, so that is more close to the real chip formation, so to say. You can see that the approximate signal characteristics is quite similar, but you have some overshoots, as you can see here with the 9255. So when you have an additional mass, you have an overshoot when you make the measurement. You also have some sort of oscillations in the red signal. So the conclusion is that the smaller the additional mass, the better the signals represent the actual process. That is important. So let's look to the last chapter now. Why should we measure forces? In order to evaluate and optimize the process through tool wear, often tool wear which is connected to the cutting force and thus decrease manufacturing cost, to understand the material behavior and machinability of different material types, to understand and optimize machine tools and inserts, to correlate force signal to certain product quality parameters. So your somehow utilizing the force measurement as an indirect measurement of your part quality, and to control the machines and processes by adaptive loops based on force signals, as we mentioned also in the turning webinar, that you can, and also in this webinar, you can directly connect your force measurement and then utilize synchronous actions in order to perform intelligent machining with your force signals. And that is being done by some of our customers. So adjustment of the cutting path, feed rate, cutting speed, so cutting conditions can be done with the input of the force signal. Adjustment of the machine electrical data and thereby changing machine dynamics can also be possible. So machine damping and stiffness characteristic, which as I mentioned is very important as affecting the part quality, and they can be adjusted depending on the input from the force signal during machining. You can build up tool wheel alarms and automatic tool changing and so on with the input of force and torque signals. You can measure the stiffness of your machine to understand and optimize the machining process during machining with the input of the force signal. You can, as I mentioned before, correlate to the final part quality. So the shape, the variation, and the statistical value, for instance, of the force measurement, it reveals the correlation to some part quality parameters. So when you can measure them indirectly, you can also control them in the closed loops. And that is again being done by some of our customers. Let's summarize again why we should measure force and torque by giving some more specific examples. As we mentioned before, you can understand and optimize the process by utilizing the torque or force measurement. You can see the force and torque levels on each insert in each rotation. You can see the torque distribution around your tool. And that is of course connected to the tool wear, the tool centering, run out, and so on. You can understand and optimize the machine process and dynamics. You can compare different setups, as you can see, through force measurement. You can understand and optimize the tool geometry by utilizing the force and torque measurements, in this case represented with the polar variables, as you can see here. And you can use the high resolution in the measurement to capture small machine and process deviations through force measurements and optimize those parameters. You can connect the measurement directly to your machine and utilize intelligent programming to make optimizations, as we also mentioned in the first session when we were talking about the turning. So I hope that this session was useful for you. Thanks for attending to this webinar. If you have further requests or questions, please feel free to contact our local KISTAR colleagues in your own country. Thank you.